on NLP and design a chatbot as part of our faculty development program. Ms. Selvabrinda completed her BE in Computer Science and Engineering from VPMM Engineering College for Women, Srivilliputur. She furthered her education by obtaining an MTech from Kalasalingam University, Srivilliputur, with a rich experience of 7 years in teaching. She has made significant contributions to the academic community. She has published 14 research papers in Scopus journals and international conferences, showcasing her dedication and expertise in her field. In addition to her academic publications, Ms. Selvabrinda has also published a patent and a copyright, highlighting her innovative approach and commitment to advancing technology. Her research interests are diverse and include machine learning, deep learning, and natural language processing. Currently, Ms. Selvabrinda is serving as an assistant professor at Ramco Institute of Technology while pursuing her part-time doctoral program at Kalasalingam Academy of Research and Education. Her dedication to continuous learning is further evidenced by her completion of the NPTEL Deep Learning course with elite status. We are honored to have Ms. Selvabrinda with us today and we look forward to gaining valuable insights from her expertise. Please join me in welcoming her for this faculty development program. Once again, we welcome you, ma'am.
Thank you, ma'am. Thank you for your nice introduction.
Thank you.
Shall I start the session, ma'am?
Okay, ma'am.
Okay, thank you.
Ma'am, am I audible?
Ah, yes, ma'am.
இல்லை இல்லை மேம் பேசலாம். Ma'am, your voice is not audible, ma'am. Selvabrinda, ma'am?
Sir, now
Is
Yes,
it
ma'am.
audible?
Yeah, yes, ma'am. Yes, ma'am. Now it is audible. Screen also visible. Thank you.
Sir, is it audible now?
Yes, ma'am. Now it is audible, ma'am.
Yes, ma'am.
Thank you.
Ma'am, are you speaking?
yes, ma'am. Am I audible?
Ah, yes, 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 ma'am.
Okay, okay.
So, good morning to all and all present here. So, first of all, I would like to extend my sincere thanks to our department HOD, Dr. M. Kalipan sir, for providing me this opportunity. to handle this session on Introduction to Natural Language Processing and its chatbot. So this is going to be the agenda of my presentation. First, let us have an introduction about natural language processing and then the differences between Gen AI and NLP and large language models, and then how the large language models get evolved, and finally with a short introduction about large language models. So we all know that only 21 percentage of the available data in the world is present in a structured format, right? So balanced data is being generated as we speak, as we tweet, and as we send messages in WhatsApp and Instagram, so etc. So by these only the data is get collected. So also the majority of that collected data exists in the textual format, okay, which is highly unstructured in nature. So to derive a meaningful and actionable insights from the textual data, it is crucial to understand the fundamentals of natural language processing. So let us see a short introduction about natural language processing. So it is nothing but a subfield of artificial intelligence. It bridges the gap between the human communication and computer understanding. And NLP, it aims to teach the human language with all its complexities to the computers. So this is what natural language processing is. So using the NLP, computers can do things like translating the languages. So in this picture, a person is speaking a language and it is converted into a numbers in which the machine can understand it. Okay, so this is done with the help of a natural language processing. So for a machine to make a sense of this natural language, surely it needs to be converted into some sort of mathematical framework. Okay, so for that we are going to do some basic transformations, and some of the basic transformations are listed here. So first one is tokenization, and next is stemming and lemmatization, then stop words removal and engrams, and finally with embeddings. I hope you all have a short idea about all these things. So making it very fast. So first one is tokenization. Tokenization is nothing but we are going to break down a long sentence or long string of text into a small chunks or smaller units called as the tokens. Correct? So it is a process to break down the long string of sentence into a smaller chunks of units called as the tokens. So these tokens are considered as the building blocks and helps to understand the context in developing the NLP model. So for that, tokenization is very much important. So here we have a simple sentence: we love NLP with the exclamation mark. So it is split up into a tokens: we love NLP and exclamation mark. Okay. So this is what tokenization is. Then next is stemming. Stemming is another essential NLP technique. Okay, this comes under the pipeline after tokenization. Okay, stemming eliminates the prefix and suffixes from the words and transform them into a root word. So consider we have three such words like programming, programmer, and then programs. So we are trying to cut the suffix of each word and we are going to derive at a common word called as the program. Okay, so this is what stemming does. It eliminates all the prefixes and all the suffixes from the words and transform it into a root words. So the main objective of stemming is to streamline and standardize the words in order to enhance the effectiveness of the natural language processing task. So next one is lemmatization. This is also the same process. It is also trying to reduce a word to its base form. But the difference between stemming and lemmatization is lemmatization purely concentrates on the context of the words and it tries to produce a valid word. Valid word in the sense, with this example, let me explain you. We have five different words here, right? So one is creative, another one is creating, and another one is created, then creating, and finally creates. Okay. So we have adjective form of words, and we have a noun form of words, and we have verb form of words. So all these things are converted into a root word called create. So this word is a valid word, right? So lemmatization focus on the context of each words and it tries to create a proper word that is a valid word, meaningful word. Okay, whereas stemming may produce a valid word or may not produce a valid word. So because stemming only cut the prefix and the suffix. So by cutting the prefix and suffix, we are not sure that we are going to get a proper word, right? So for example, see here, we have two different examples. One is studies and another one is studying. Okay, so here we are trying to cut the suffix. So here es will be cut, here ing will be cut. So first term produce a word that is not a valid word. Okay, study is not a valid word and the study is a valid word. So stemming may sometimes produce a valid word and may not produce a valid word, whereas lemmatization focus only on the context and it produces a valid word always. So lemmatization is better than stemming always. Okay. So this is another example of lemmatization. And next one is the stop words removal. So stop words removal is also a pre-processing step in NLP. Okay, this follows the stemming and lemmatization. So in a particular sentence or a language, we may have some words called as a fillers. Okay, that is going to fill the sentence. Okay, so those words may be a conjunction, maybe a proposition, or whatever it may be. So that words does not going to give any meaningfulness to the sentence. Okay, so those words are called as the stop words, and these stop words can be eliminated in order to reduce the computation also. So this can be this all the process can be done using the NLTK library, that is Natural Language Toolkit. That is a library used to perform the natural language processing task. So next one is the n-grams. So n-grams is nothing but it is a sequence of n words from the given sample of text. If you have a sample of text and that we are going to get a sequence of n words. So n is nothing but a combination of words together. That is co-occurring words, you can say. In a short, co-occurring words. Okay. So why we are using n-grams means in order to capture the information such as word order. So how the words are, so for example, if a word this comes means it will be followed, mostly it will be followed by this is or this could be. So like that the words this will be followed by another word. So the set of co-occurring words will be identified using n-grams. So one such example is, so consider this sentence, this is a sentence. Okay. So if we keep n value as 1 means, yeah, the words are split up in the sentence, each word gets split up as a single word. If n is equal to 2 means in the sentence the word gets combined as 2. So bigrams, this is called bigrams. So this is a and then yeah sentence. So if n is equal to 3 means the words are combined three times. Okay, so this is what n-grams. This is used to capture the word order. So next, last basic transformation is embeddings. So embeddings is nothing but we are going to transform the textual data as a numerical representation. Okay, so the machines cannot understand the textual data as such. So we have to convert the textual data into the numerical representation. Okay, so for the NLP task, to perform the NLP task. So we have four such embeddings. We have many embeddings. So out of which we are going to discuss only four. First one is one hot encoding. Already from the name itself, we know that one hot encoding is nothing but we are going to provide a vector representation for words in the format of zeros and ones. So that is one hot encoding. And then count vector. It is nothing but we are going to count the frequency of the words. So from the name itself, it is explanatory. So second one is count vector. And third one is TF-IDF. It is nothing but term frequency, inverted document frequency. So let me explain one by one. So third one is TF-IDF. This is going to identify the importance of a term. So that is the main thing of TF-IDF. And fourth one is word to vec. It is also called as word embedding. So let us discuss one by one. So one hot encoding, as I said earlier, it represents each word in the form of zeros and ones. Okay, so this is an example sentence given here. So this is the red column. So where we have the word red, it is represented as 1 and balance all the words are represented as 0. So this indicates the one hot representation. So if a word is present, it will be indicated as 1. Otherwise it is indicated as 0. So this technique will not be suitable for a language with a large vocabularies. So for example, if I have a 10,000 words, imagine in my dictionary I have 10,000 words. Okay, so I cannot provide one hot encoding for all those 10,000 words, so it is somewhat complicated, right? So because the vectors will be huge, even though this technique is very simple, but it may not be suitable for the sentence having the large vocabularies. So second one is count vector, or it is also called as the bag of words. So here we are going to count the frequency of the words and give the vector representation for the words. Why we are giving vector representation for the words? Because the model, machine learning model, will understand only the numbers, only in the form of numbers. So all the text data should be converted into a numbers. Okay, so here the occurs two times. So the frequency of the word the is 2 and all other terms occur one time. So all the frequencies will be 1. Okay. So this is the bag of words. And next is TF-IDF, term frequency inverted document frequency. So as I said earlier, so it is going to consider the importance of a given word, how much that particular word is important to a document. So that is TF-IDF. So consider TF-IDF is calculated using the formula TF into IDF. Okay. So TF is nothing but total number of occurrences of a term in a document divided by total number of terms in the document. So this is a formula for term calculating the term frequency. Okay. So IDF, inverted document frequency, is log of total number of documents in the corpus divided by number of documents with the term T in them. So let me explain this with an example. So consider these two sentences. So first sentence is the car is driven on the road. Okay. So second sentence is the truck is driven on the highway. Okay. So how the TF-IDF is calculated means all the words present in the sentence are written separately. Okay, the car, truck is driven on the road, highway. So everything is written separately. Okay, we are going to find the TF. What is the formula for TF? TF is number of occurrences of a particular term. That is the count of a particular term in a document divided by total number of terms in that particular document. So we have two such documents, A and B. Okay. So the occurs how many times in the document A is given in the numerator. So in the first sentence, the occur two times. Okay. So here I have splitted the word the. So I have given the counting separately. Okay. So first one is the count of a term divided by total number of words in the document. So we have 7 such words in the document A. Okay. So similarly for car, in the first sentence there is no word called truck, so it is given as 0. Also in the first sentence there is no word called highway, then it is given as 0. So similarly we are going to calculate the TF for each word in each document. Okay, this is the calculation of TF, and then IDF is calculated by log of, in the numerator, how many documents totally we have this represented in the numerator. So we have two documents A and B. So log of 2 divided by how many documents having the word the. So in the previous example, the is present in A document, the is present in B document. So two documents are having the word the. So log of 2 by 2 is log of 1, which is equal to 0. Okay. So in second case, car word. So we have to find the IDF calculation for the word car. So log of total number of documents is 2 divided by in how many documents the word car is present. So car is present only in the document A, and also it is presented one time. So 2 by 1. So log of 1 will be 0.3. So this is the calculation for IDF for all the words. Okay. So TF into IDF means we have to combine both. You multiply both. Okay. TF into IDF. So for the document A, if I am going to calculate TF IDF means 1 by 7 into this 0, answer will be 0. Then 1 by 7 into this 0, answer will be 0. Similarly, here 1 by 7 into this 0.3, the value will be this thing, and 0 into 0.3, the value will be 0. So this indicates which word and all important. So those words are getting the higher vector representation more than 0. Okay. So which indicates that the word car, the word truck, the word road and the word highway is more important in these two sentences. Okay, clear? So this is TF-IDF calculation. So TF-IDF is going to find the importance of a term in the sentence. So that is the TF-IDF calculation. So next one is word to vec. So up to now we have seen 3 such embeddings, and these 3 embeddings are not concentrating on the semantic similarity between the words. Semantic in the sense, if we have 2 words having the similar meaning, so those embeddings should be somewhat similar, correct? So as a logic, if we have 2 different words with the same meaning or same context, the two words should have a same embedding. So that is the logic. But these semantic similarity is missed in the first three things. So the fourth one, word to vec, is going to capture the semantic relationship. Okay. So word embedding work as a mapping of words in vector space. So consider this is a vector space, a dimensional space, or it is considered as a vector space. Here we are going to map the words. So men and women, king and queen, both are somewhat semantically related words. So these two words should be related, semantically related. Okay. So this is going to be found out by the word to vec word embedding. Okay. So the objective function of word to vec is word which have similar context to have a similar embeddings. Okay. So for example, here in this sentence we have a term called word called kid. Here in this sentence we have a word called child. So both are focusing, denoting the same things. Word and kid both are the similar context words. So they should have a similar word vectors or vector representation because they have a similar context. Okay. So word to vec have two architecture. One is continuous bag of words and another one is skipgram model. So we have two such architectures in word to vec. So CBOW is nothing but continuous bag of words and skipgram is another thing. So the difference between these two is CBOW is going to predict the target word from the context word. Means so consider this is a sentence. The quick brown fox. So we have left a blank here over the lazy dog. So this is a sentence. So this blank should be filled by a word. So we can fill this word in our guess. Okay. So this word can be filled in our guess, but this word should be the target word. So what we are trying to predict is the target word, and balance all other words are considered as the context words. So CBOW is nothing but predict the target word based on the context words. Whereas skipgram is we have the context word and we have the target word and we are going to predict the context word. This is somewhat complicated than this CBOW, right? So finding a single word is easy. Finding a 7 or 8 words is very much difficult. So scriptgram is predicting the context words from the target word. So let me explain the working of CBOW with an example. So it will be understandable to you. So consider this sentence, hope can set you free. So this is a sentence. Okay. So one of the important thing in CBOW is we have a context window. We have a concept called context window. So context window size can be fixed by us. So context window size in this example, I have fixed it as 3. Means it has to consider 3 sentences. This window has to consider these 3 words. Okay. So consider this can is not present here. This can is not here. The word can is not present here. Assume. So this hope and set is considered as the context words, and this word should be found out by us. We have to find what word will come here. So assume this can is not present here. Okay. So how we do this means, first we have to write the one hot vector of the context words here. So we have context word hope, we have a context word set. So hope one hot encoding is written here and the set in one hot encoding is written here. Okay. So hope means one hot encoding will be under hope we have the number as 1, balance all others are zeros. One hot encoding of set means the set is present in a third place. So third place will be given a number 1 and all others are 0, right? So this architecture looks same as the deep learning architecture. We have an input layer, we have a hidden layer and output layer. This is similar to deep learning architecture. Okay. So this one hot encoding is mapped with the context window. We have 3, a context window of size 3, right? So this 3 will be presented here. So the input one hot encoding of the input context word will be mapped with the context window and we are going to get the predictions. So this is the prediction for the word can. Okay. So we have actual actual data with us and this is our prediction. We have to combine this prediction with the actual. If both are correct, then our prediction is correct. Otherwise, we have to update the weights as we do in neural network architecture. In neural network architecture, we have an input layer, we have a hidden layer, and we have an output layer, right? So in between, we have weights and bias concept. So if the predictions and the actuals are not matched, if there is more error, we have to backtrack. That concept is called back propagation. So we have to backtrack and we are trying to adjust the weight in order to match the prediction as well as the actuals, correct? So the same procedure followed here. So this is the predictions of the word can, and this is the actual value of the word can, actual encoding one hot encoding of word can. So both are same. So the answer is correct. If not, we have to update the weights again. Okay, so next, this context window, no, this will move till the end of the sentence. It will take three words and it will move till end of the sentence. Okay, this is the working of CBOW. So here we have predicted the target word. So our aim is to give the word embeddings. So that is the thing we are speaking till now. Embeddings only we are focusing till now. So prediction, why I am going for prediction, and after that why I am dealing with word embeddings means, so once the prediction is obtained and if it is correct, so the weights used in between can be taken for the vector representation, word vector representation. If this answer is wrong, then we have to adjust the weight and we have to find the correct answer. Okay, so this weights, the final weights will be the word embedding vector representation. Okay, so consider this. So we have a prediction and we have a actuals, both are correct. So this weights can be the final weights. Okay, so these are the weights. Consider, assume I have given roughly W00, W01, W02 will be the weights of this thing, this neuron, and this next, this row W1011121314 will be the weights of this neuron, and then W2021222324 will be the weights of this neuron. Okay, so weights after the training, what weights we got, and we have to keep the one hot vector of all the words. Hope can set you free. We have to keep the one hot vectors of all the words. Okay, so how to find the vector representation of the word hope is, we have to multiply the weight with the one hot encoding of the word hope. If I want word embedding representation for the word can means, I have to multiply this weight with the one hot encoding of the word can. So this is the concept to get the word embeddings of each word using SIBO, continuous bag of words. Okay, so here this weights are multiplied and roughly we got some word embeddings. Okay, so this word embeddings are the vector representation of the word hope. So the vector embedding representation for can may be different from the hope. Okay, so I have given the justification here, the reason behind predicting the words instead of generating the embeddings. So initially we have not generated the embeddings, we have only predicted the words. Why so? Because the embeddings are extracted only from the weight matrix. So first we have to predict first and then we have to generate the embeddings. Okay. So next is skipgram. So this is the reverse process of SIBO, dead opposite of SIBO. So we have a target word with us and we are going to predict the context words. Okay, so same procedure. So next is the application of natural language processing. So natural language processing is applied in language translation, smart assistant, as you all know. Okay, so it is applied to document analysis where and all the text data is present. So for there, natural language processing task can be done, can be applied. Okay, so online search, predictive text, automatic summarization, social media monitoring and chatbots, so and so. So next is Gen AI versus NLP versus LLM. So for the past 1 week, you'll all having heard about this Gen AI. Okay, so not much information to be conveyed now. So generative AI is nothing but it's going to get the data and we are going to apply the Gen AI and we are going to generate a new content. Okay, the data can be a text, the data can be in the form of a post, the data can be in the form of the image, the data can be in the form of audio. So anything, whatever it may be, the data when it is fed into Gen AI, it can create a new content. But that new content should consider the characteristics of the original training data, but it should not replicate the training data. Means the new content is entirely different from the training data, but it takes some characteristics from the training data. So that is what Gen AI is. So next is natural language processing. Already we have seen. So it is designed to understand, interpret and generate the human language. Okay. So NLP is enhanced to generative AI. NLP only enhanced to generative AI. And next thing is large language models. So NLP plus Gen AI together constitute large language models. Okay. Nothing. So NLP means it is going to understand the context. Okay. Gen AI is going to generate something. So both the task are done by large language models. It is going to understand the context and it is going to generate something. And that too generating a new content. So that is large language models. Okay. So next is transition from ELIZA to large language models. Means how the large language models evolve. Okay. So this is the evolution of large language models over a period of time. How large language models evolve is portrayed here. So first language models start from the year 1967. Okay, so ELIZA, it starts from ELIZA. It is the first chatbot. Okay, and after that in 1970, a programming language SHRDLU is developed, and then 1980 Excalibur is developed, and in 1988 RNN is developed, and then in 1997 LSTM is developed, and 2017 the concept of transformer arises. Okay, transformer is well explained by Mani sir from Geologics on Saturday's class. So I hope you all get a good idea in transformer, right? It consists of encoder and decoder architecture. Okay, so next one is 2018 BERT and GPT came in. So this is the starting point of large language model. So from here only large language model started. Okay, and after that we have GPT versions 2, version 3, 3.5. 3.5 will support for chat GPT. Okay, and then in 2022 we have a large language models called PALM, Instruct GPT, Chat GPT. Okay, so 2023 LLAMA, GPT-4. So all these things, how the large language models get evolved over a long period of time. So I'm going to explain about the ELIZA better, and then RNN, and then LSTM. As you all already know transformers, I am not going to touch this concept. And then finally, we are going to end up with the large language models. Okay. So first thing is ELIZA. It was introduced in the year 1967. It is a first built chatbot by humans. Okay, this is the first chatbot. So ELIZA is a yearly natural language processing computer program developed at MIT by a scientist called Joseph Weizenbaum. Okay, so ELIZA enables the human-computer interaction. So it is a chatbot, right? So it enables the human-computer interaction. So it creates an illusion of the conversation by rephrasing its user statement as a questions back to them. So nothing but, so consider these two
Exam
sentences.
31st.
So here you is a human being and Eliza is this chatbot. Okay. So human is asking men are alike. So Eliza is answering what is the connection do you suppose? So from the statement that is given by the human, Eliza tries to frame the question. Okay, it creates an illusion of the conversation. So this what happens at that time. Okay, a small uh, yeah, demo is given here. Eliza the Rogerian therapist. So this is a website you can search in Google. So here I have given a statement, had your breakfast, to this Eliza. It is responding, why are you concerned about my breakfast, right? And then I am saying a statement, my favorite food is biryani. It says, do you have any psychological? So from the statement, it tries to frame the question. So that is the conversation happened at that time using ELISA. Now ChatGPT is more advanced, right? Because it is pre-trained. So next, a little bit of information about recurrent neural network. So recurrent neural network uses the concept of neural networks. Okay, neural networks emerges in the year 1980. It mimics the uh, behavior of the human brain. Okay, it consists of interconnected neurons and it learns from the large volume of data. Okay, and it uses the complex algorithms to train a neural network. Okay, we all know this. So neural network has many variants of algorithms and in which we are going to focus only on RNN. Okay. So this is a neural network concept. We all know that this is the input layer, this is the hidden layer and this is the output layer. Okay. So in between this connection, in this connection we have weights and a bias. Okay. So this is a neural network architecture. And then why we are going for neural network? We have n number of algorithms, deep learning algorithms in neural networks. Why we are going for recurrent neural network means because neural network will process the textual data in a efficient manner. Okay, so for the three things we are going for recurrent neural network. One is it can handle the sequential data. Number one, sequential data is a time series data or it could be a textual data, and then it considers the current input and also the previously received inputs, means it is bidirectional. Okay, so if I have a sentence like he is a boy. Okay, so I have left a blank in between. So he is, I have left a blank, a boy, sorry, boy. Okay, that blank should be filled up. So if we consider only in the forward direction, we may forget to consider the backward direction. Okay, so if we consider a sentence both in forward and backward direction, and if we find the context of the word, context of the words, then only we can find, we can predict a particular word. So this RNN considers both the current input as well as the previously received inputs. Okay, and then third thing, it can memorize what are all the information, what are all the words it is reading. It can memorize all the things, and it also can memorize the previous inputs because it consists of an internal memory. So for these three things, we are going for recurrent neural networks. Okay, so this is a simple architecture of recurrent neural networks. So it consists of a feedback loop, means the name itself is explanatory. It is recurrent, means it is recursive, repeated process. Okay, so repeatedly it has a feedback loop because the output of the previous one will be the input of the next one. So here there is a connection between previous and the next thing, so the feedback loop is here. So this is a theory part, what I have said before. So RNN is an important variant of neural networks. Okay, it can process the sequential data. And previously we have a traditional feed-forward neural networks, and that traditional feed-forward neural network is unidirectional. It has no feedback loops, right? It will only flow in only one direction. So it fails to see the words that are behind. It fails to understand the context, the words in the opposite direction. So that is the drawback of the feed-forward neural network, whereas RNN has the flow of information in bidirectional. Okay. So it has two inputs. One is the past input and the present input, current input. Both will be given to RNN. In RNN, we have a concept called cell, and to that cell, the information, the input will be given, and this cell has two inputs. One is the input what we are providing, that is the present input, and the previous computation output. So both will be passed as input to the RNN cell, and it has a feedback loop. Okay, so this is the diagram for RNN. So here this is the current input, xt is the current input, xt minus 1 is the previous input, and xt minus plus 1 is the next input. Okay, so here the output of this cell is given as input to this cell, and also the current input will be passed. So two things are given as input to this particular cell, one is past and present. Okay, so u, w, v, these are all weights. Okay, so this is the output uptime. So this is a recurrent neural network. It consists of a feedback loops, and it can handle the sequential data, and it considers the past and the present information. So this is a simple example. So consider this information. Tom is playing cricket in the garden, right? So our human brain is capable of storing the keywords. Okay. So what are all the keywords present? So Tom, then cricket. What are the important words? Garden or park, anything. So the brain, human brain is capable of memorizing everything, and it can ask the question. Many such type of questions human brain is able to ask by remembering the keywords. Whereas the same concept is present in RNN. It can store all the key information in its memory as like human brain. Okay, so it can also answer the questions based on the context. It is capable of predicting the next word based upon the context both in bidirection. It will search the words in both the direction, and it will understand the context in both the direction, and it will predict the next word or a next set of words. So even though RNN is very good at predicting the target word, it has some limitations while dealing with the long sentences. Okay, this RNN suffers from long-term memory loss. Okay, so consider if I have 10,000 documents. So in the first sentence, in the first line of the document, I have a word called chocolate. So I have mentioned an important chocolate. And in the 500th place, if I am repeating the name of this that chocolate means, RNN cannot keep this thing in mind because it is a long sequence of data. So RNN, as such, it processes the words. It will forget everything. So it cannot retain all the things that is stored in the memory for a long period of time. So that is one of the issue with the RNN. So that issue is called as a vanishing gradient problem. So RNN is not good at retaining the memory for a long time. So to deal this problem, the concept came called long short term memory. Okay. So this problem can be overcome by this LSTM. So this is considered as the primary advantage of LSTM. Okay. So LSTM can be able to remember the information for a long period of time, and it can be able to resolve the vanishing gradient problem that is faced by RNN. So for that, this LSTM has a concept called gate. Okay, so LSTM is introduced in 1997. So we have seen in the diagram, evolution of LLM diagram. And then this is a specialized type of RNN architecture, and it has a concept called gates to regulate the flow of information. Okay, so what information should be memorized and which can be discarded, and what should be given as the output. So everything is determined based on the gates. So the gates is the main thing that is present in LSTM to regulate the flow of information. So we have three such gates. One is a forget gate, next one is the input gate, and third one is the output gate. Okay. So forget gate, it forgets the irrelevant information. So what are all the information we not needed, so that information can be forgotten. And then input gate is going to add or update the new information. And then output gate, it's going to pass the updated information. So this is the working of these three gates. And this is considered as the LSTM cell. Like as such in RNN we have a cell, the same concept in LSTM we have an LSTM cell. Next thing, so this we have a two such variables. One is a C and another one is H. Sorry. So H is a hidden state. We have input layer, hidden layer, and output layer. So H indicates the hidden layer. And C is nothing but it is a cell information, or it is called as a cell state. Okay, so this is the current cell state at timestamp t, current timestamp t, and this is the cell state at the previous timestamp. And this is the hidden state at timestamp t, and this is the hidden state at the previous timestamp. Okay, so this hidden layer is used for a short-term memory. Whereas in LSTM, we have one more variable called C. This is used for a long-term memory. This C is missed in RNN. So this is the one of the plus advantage of LSTM. So LSTM has a cell information or a cell state that is capable to store the information for a long period of time. So this C is considered as the long-term memory. Okay, so that's all. So forget gates means already I said this decides what information should be removed and what information should be kept. So that is the forget gate. Okay. So forget gate equation and all, just go through the equation. Okay. So forget gate equation is the input is multiplied with the weights, its corresponding weights. So in a neural network architecture, once again, neural network architecture, we have a connections in between, and in this connection we have a weights in between, right? So input is multiplied with this weight and reaches the next layer neuron. Okay, So the same concept is followed here. So input into its corresponding weight plus the hidden neuron into its corresponding weight. So both are get added and a sigmoid activation function is applied over it to get the answer. So if here we are using the sigmoid activation function. Okay, sigmoid activation function, it scales the value between 0 to 1. Sigmoid activation function will give the value between 0 to 1. If the value is 0 means, the forget gate value is 0 means you have to forget everything. That information is not needed. Okay, if an information or if a sentence or if a word is passed into the LSTM cell, that information is important or not, that is identified by this forget gate. The forget gate, while applying the equation, if the value is 0, then the forget gate eliminates everything. It forgets everything. If not, if the value is 1, it forget nothing, means it keep the information as such. So this is the forget gate. So next one is input gate. Input gate is used to update the cell state value. So this is the cell state, correct? So this is the cell state. So to update the cell state value in the input gate is used. Okay. And also input gate is used to quantify the importance of the new information. If any new information is added, we want to add something, so that is also possible using the input gate. So input is nothing but we are going to give the input, and also it is going to consider the new information, and it is also going to update the cell state value. So the same equation for input gate, also the same sigmoid function also. So value between 0 to 1, if 0 comes means the input will be passed, sorry, input will not be passed. If the value is 1, the input will be passed. So that is the input gate. So next, consider this sentence. Bob knows swimming. He told me over the phone that he had served the Navy for 4 long years. So consider these two sentences. Okay. So it seems that this Bob knows swimming is not that much important than this sentence. He has served the Navy is much more important than Bob knows swimming. Correct. So this important information should not be forgotten. Okay, this should be kept in memory for a long time. So for that, input gate will add this new information for further computation. This he was served in the Navy should not be forgot by this LSTM cell. That is an important information. This should be kept for a long time. So how to update the new information? So same formula, input into its corresponding weight plus hidden state into its corresponding weight, and tan h is applied over it. Tan h scales the value between -1 to +1, which means -1 means the information should be subtracted from the cell state, means the information is not needed. If the value is positive means the information will be added to the cell state, the new information. Okay. So this is the concept for adding the new information into the input gate. Okay. So the new information also cannot be added directly to the cell state. So there is a need of an update equation. So this is the update equation to update the new information. So what is the equation means? Forget gate into the cell state, current cell state plus the input into the new information. So by this only the new information can be updated to the cell state. So last one is output gate, the same equation, input into weight plus hidden state into weight, and applying a sigmoid over it. So we get the output. So overall, what the process we have seen till now is depicted in this diagram. So here, consider this as a forget gate. Here we have a FT, this is a forget gate. And IT, this is the input gate. And CT is the cell state. Okay. Then finally this is the output gate, sigma. So this is the output gate. Okay. So the input into its weight is passed, hidden state into its weight is passed, sigmoid function is applied over it. If the sigmoid answer is 0, it will forget everything. If it is 1, it will add the information to the cell state. Okay. Then again the input along with the weight is passed plus hidden state into the weight is passed, and sigmoid is applied over it. If the answer is 0, the input will not be passed. If the answer is 1, then the input will be passed. Again the tan h for adding the new information. If the tan h value is -1, the information will not be updated. If it is +1, the information will be updated to the cell state. Okay. Then input into weight plus hidden state into weight is applied a sigmoid function over it, and this will be the output to the cell state. Okay, so this is the overall concept of input gate, output gate, and the forget gate that is present in LST. So this is one particular cell, and this one particular cell is explained here. So similarly, we may have many sequence of inputs in LSTM architecture. So next, emergence of large language models. Okay, so large language models. So let me start with an example. So consider two different person, a father and a child. Okay, a father is saying his child, "I am so hungry. I would like to have." Like that, he stops. He left a blank there. So the child says, the answer is biryani. So actually, father may like to have some other foods, maybe like chapati or maybe like juice or anything the father may like to have. But this is a random guess that is given by the child as biryani. So he gives this answer by hearing the conversation that is happening in his home, right? A small child that is giving this guess by hearing the conversation in his home. So the answer that is predicted by combining the statistical probability along with some randomness to predict the next word or a next set of words based upon the previous conversation is called as a stochastic system. Okay, stochastic system is nothing but the answers are predicted based upon the probability and based upon the random guess. So that is a stochastic system. So the same way LLM work, large language models, is also a stochastic system. So based upon the probability and based upon the randomness or based upon the guess, it will predict the next word or a next set of words based upon the past conversation what they had previously. Okay, so this is the LLM, large language model. So the name itself is self like explanatory. It is large language models. Large in the sense it uses a large amount of data, large huge sets of data. It is trained on huge sets of data, and also it has a trillions and billions and trillions of parameters with it. Okay, so that's why the name large is given to this large language model. Okay, so this large language model uses the transformer based architecture, and it is equipped with transformer means we have encoder as well as decoder. Okay, already you all know this. So it is equipped with the trillions of parameters with it to capture the complex patterns in order to predict the next set of words in a sentence. So the main thing is we are going to predict the words. That is the main thing in all this architectures. Okay. So next thing is it is trained on a huge, not only predicting the next sentence, LLM will also going to generate something, generate some new text based on the past conversation. Okay. It is trained on a huge set of data, maybe a Wikipedia articles, Google News articles, online books, etc., codings. So in all these things, the LLM is trained. Okay, so this training is given in the form of a self-supervised manner or a semi-supervised manner. Already we all know that semi-supervised means the input supervised plus unsupervised. Okay, supervised means we are feeding the input and we are giving the output and we are trying to make the machines to learn, that is supervised. Unsupervised means we are giving only the input and make the machines to identify the patterns or make the machines to group the data. Okay, so semi supervised means it will have small set of supervised learning and it will have small large set of unsupervised learning. So this training LLM requires self supervised or semi supervised learning techniques. It can learn on its own. So this LLM or AI driven system that specializes in generating the code from the natural language inputs. Then some of the examples of LLM is ChatGPT by OpenAI and LLAMA by open source. This is the large language meta AI model, and then Palm 2 by developed by Google. Okay, so the heart of ChatGPT is the large language models. Okay. So Gmail autocomplete can also be an example for this. So next one is reinforcement learning with the human feedback. So from the name we can say that reinforcement learning is learning with the mistakes. Okay, reinforcement learning is nothing but learning from the mistake. Okay, so also reinforcement learning along with the human feedback. So this concept is involved in ChatGPT. Okay, ChatGPT, while training the ChatGPT, this reinforcement learning with human feedback concept is given. Okay, so let me say this with an example. So it's the same example again, a parent and a child, small child. Okay, the child may got the superpower and he is able to hear the conversation from his nearby houses, from his schools and from his colleges, and he may be hearing all the conversation. Okay, so if the father is saying, "Don't teach too much sweets, else," like that, he stops. So the child may give different answers for that. "I will punish you with a rod. Your stomach will hurt." So he is giving two different answers, two, three different answers for a particular sentence. Okay, means he had heard the conversation from his nearby, from all the nearby schools, colleges, and the nearby houses. So for that, he is giving this responses. So the person, that the father, is going to teach the child which one is good and which one is bad response. He teaches the child like that. Okay. So this concept is involved in training a ChatGPT. So while training ChatGPT, OpenAI uses this reinforcement learning with the human feedback. So it assigns some group of humans to make this ChatGPT less toxic. Okay, the responses should be a good one. The responses should not be a toxic one. So in order to train the ChatGPT, the OpenAI uses this concept called reinforcement learning with the human feedback. So this is one such clipping that OpenAI uses a huge workforce of humans to make this ChatGPT less toxic. Okay, so ChatGPT is pre-trained already with a lots and lots of data. So for to make it less toxic, this has been done by OpenAI. So thank you. That's all from my side. If any queries, you can ask me. Any queries?
Hello, good morning, ma'am.
Good morning, ma'am.
Ma'am, what is in the activation function, ma'am?
Activation functions can be a sigmoid activation function. We have softmax activation function. We have ReLU activation function. This is going to activate the neuron. So in a output layer, so consider if you are going to do a binary classification problem, means we have in output layer we have two neurons. Okay, so to for providing the output. So binary means either true or false. Okay, you are going to give the answer as true or a false is the matter. So this activation function is going to activate the neuron to produce the output. Either it is true or false.
Okay, okay, thank you.
Okay, thank you. Thank you.
Madam, any demo is available?
Sir, we'll try next time, sir. Demo is not available now. In the
Okay.
next session, I will give the demo, sir.
Okay, okay, madam. Okay, thank you, thank you.
Thank you, sir.
Hello, ma'am.
Yes, sir.
Yeah, ma'am, can you please share that like the slide? Just open that slide where the activation function you explain the states, right? Particular
Yes,
states.
sir. Yes,
Yeah,
sir.
please can you please open that slide?
1 second, sir. Under LSTM.
LSTM, LSTM.
Okay, okay. So this thing, yes, sir.
Next one. I guess 65 slide number 64.
Okay.
Yeah, yeah, ma'am. Here the activation function is sigmoid, right, ma'am?
Yes, sir.
Yeah, and when the sigmoid has output 1, then it will be considered.
Yes.
Yes, ma'am. Ma'am, when the other activation function like ReLU and are used, so can you
Yes.
please tell me
So,
what will be the matrix for it?
sir, ReLU will scale the values between 0 and max value. So, if
Yes,
for a sigmoid we have 0 to 1, right? Either we
yes,
get a
ma'am.
value
Yes,
0 or we get a value 1. So, in
one.
ReLU we get a value as 0 and maximum value. Out of 0 and maximum value, which one is, I mean, out of two set of values, which one is maximum? That will be the answer for ReLU. It will display the maximum value.
Okay, okay.
Thank you, sir.
Thank you, thank you.
Thank you for your nice session, ma'am.
Thank you, sir. Thank you. Thank you so much, sir. Thank you for providing me this opportunity, sir, to share my things. Okay. Thank you, sir.
Thank you, ma'am.
Okay. Thank you, sir.
Let us conclude today's session. Good morning to one and all. On behalf of Ramco Institute of Technology and Department of Artificial Intelligence and Data Science, I extend a heartfelt vote of thanks to all those who have contributed to the success of this faculty development program. First, I would like to express our sincere gratitude to distinguished resource person, Mrs. Selvabrinda Ma'am, for taking time to share her invaluable insights and experience with us. Your vision and dedication have been instrumental in bringing this program to fruition and providing us with invaluable opportunity for growth and learning. Thank you, ma'am. I would like to extend my sincere thanks to our beloved HOD, Dr. M. Kaliappan sir, whose encouragement and resources have made this program possible. Thank you, sir. A special thanks goes to all the participants for your active engagement and enthusiastic participation throughout the session. Finally, I would like to thank organizing committee and all the faculty members of our department for their active support in organizing this FTP. Thank you all.
ஸ்டாப் பண்ணிடலாமா?
ஆமாம் சார், அவ்வளோதான்.